In this video, I'm going to share what is collision theory and what is transition state theory.
What is collision theory? Collision theory assumes that for a reaction to occur, reactant molecules must collide with an energy greater than activation's energy, and the colliding molecule must also have correct orientation in order for the reactions to occur. So what is activation's energy? Activation's energy is the minimum energy of collisions required by colliding molecules to initiate a reaction. Where should we label the activation's energy in the energy profile diagram? Activation's energy refers to the minimum energy required by the colliding reacting molecule in order to initiate a reaction. From the diagram, we can see that the minimum energy the colliding reacting molecules must have in order to climb over the energy barrier to react and to form product is equal to the difference between the energy level of the reacting molecule and the highest point of the curve. Hence, the difference between the energy level of the reactant and the highest point of the curve is the activation's energy of the forward reaction. According to collision theory, the second requirement for an effective collision to occur to result in the formation of product is to have correct orientation. Like for example, in these reactions, hydrogen molecule react with iodine molecule to form hydrogen iodide. If the hydrogen gas and iodine molecule are colliding side to side, this orientation is improper and therefore will not result in formation of product. However, if the hydrogen molecule and iodine molecule are colliding one from the top and one from the bottom, so the orientation is correct, and these orientations of collision, if they are colliding with energy equal or greater than activation's energy, then the product hydrogen iodide will be formed. Though collision theory explains some important features of a reaction, but it does not explain the role of activation's energy in a reaction. Transition state theory explains collisions between two reactants resulting in formations of an activated complex or transition state. An activated complex is an unstable grouping of atoms that can break to form products or revert to reactant. For example, in a reactions between hydrogen molecules and iodine molecules, if the reacting molecule are colliding with energy equal or greater than activation's energy and having correct orientation, this activated complex will be formed. Since this activated complex is of correct orientation, then the activated complex will break to form the product hydrogen iodide. However, if the hydrogen molecules and iodine collide with energy equal or greater than activation's energy, but the orientation is not correct, this is the activated complex that is being formed. Since this activated complex is not having the correct orientation, then it will revert form the reactant hydrogen gas and iodine molecules. One thing to take note is activated complex or transition state has higher energy than reactant and product. So where should we draw the activated complex or transition state in the energy profile diagram? We should draw it at the highest or maximum energy point in the energy profile diagram. Now we move on to look at for exothermic reaction. If given the reaction with reactant A plus reactant B to produce product C and D with the enthalpy change equal to -100 kJ per mole and activation's energy for forward reaction 300 kJ per mole, how to determine the activation's energy for reverse reaction? First, we must label the activation's energy for forward reaction. For forward reaction, the activation's energy is between the reactant and the transition state or activated complex, which is equal to 300 kJ per mole. For reverse reaction, then now the C and D become the reactant for the reverse reaction. Therefore, the activation's energy for the reverse reaction should be labeled from C and D to the highest point in the energy profile diagram or to the transition state. So this is the activation's energy for the reverse reactions. And how to calculate the activation's energy for the reverse reaction? We can calculate the activation's energy for reverse reaction by minus the enthalpy change from the activation's energy for forward reaction. So that is equal to 400 kJ per mole. For endothermic reactions, how to determine the activation's energy for reverse reaction? If given the reactions have reactant V plus reactant W react to form the product X plus product Y, and the enthalpy of the reaction is positive 100 kJ per mole with forward reaction having the activation's energy equal to 400 kJ per mole. To determine this, again, first we need to label the activation's energy for forward reaction. Again, for forward reaction, the activation's energy is the energy difference between the reactant and the transition state. So label it as 400 kJ per mole. To determine the activation's energy for reverse reaction, first we need to draw where is the activation's energy for reverse reaction. For reverse reaction, now the product X and Y become the reactant. And to draw the activation's energy for reverse reaction, it is referred to the energy difference between X and Y and the transition state. So this is the activation's energy for reverse reaction. To calculate the activation's energy for reverse reaction, again we apply the formula enthalpy change minus from the activation's energy of forward reaction, that is equal to 400 kJ per mole minus 100 kJ per mole of enthalpy change to give us 300 kJ per mole as the activation's energy for the reverse reaction.